let's begin our class today. Okay. Before starting class, do you have any question? Okay, if you do not have, then maybe I will start from here. So in the last class, we stopped in this slide. Actually, I'm going to come back this slide, and then I will explain later on. Just let's start from this one first. Okay. So this one is we're gonna discuss the energy band diagram a lot throughout the class. So to understand the energy band diagram, we need to understand some general concept for the energy band diagram. So as you know, this one shows the general energy band diagram. We have the conduction band, we have a valence band. Okay, so now, as you remember, is that the electron, once they going on the conduction band, they start to flow through this conduction band. Now, if the electron get energy, then now is that for this direction, electron moves. So in other words, if we just compare the energy here and then here, the electron located in here get this amount of more kinetic energy compared to the electron in the conduction band. Okay, so in terms of electron, in this direction, energy is increased. Okay, now if you look at the concept for the hole, for the hole, most of the hole remain at the top of this valence band edge. Okay, once the hole get the energy, now hole moves in this direction. So in other words, is if we look at the energy difference between the hole, for example, located in this location, to this valence band, the hole located in here get this amount of kinetic energy more compared to this valence band edge. Okay, so this concept is very important throughout our class. Okay, and then now in here, another concept is we're going to correlate this one with the potential. So when you look at the potential, in this direction, if you apply the negative potential, okay, if you apply the negative potential, later on is that we will see the energy going to increase in this direction. Okay. So similarly, if you apply the positive potential, your energy going to increase in this direction. Okay. So this concept later on also we're going to look at, especially when you apply the bias between the PN diode and then how the energy band diagram going to be realigned depends on our applied bias. Okay, so I will visit this one again. So now in here is that this one shows the relationship with the energy and the electric field. So for example, if we start for the electron, the potential energy we can calculate from the electron is negative charge Q multiply with the potential. Okay, and then for example, let's say if you choose the particular potential energy, in here is that from EC to the E reference. So simply E reference is going to be certain energy level. Let's say we choose as a reference. And then in here is potential energy up to the conduction band. We can calculate from this equation. Now we're going to correlate these two equations so that in terms of potential V equals with this energy difference. Okay. Now, as you know, is electric field and potential will have this kind of a relationship. Okay. So in other words, that if we derivative of the potential, then from there we can obtain the electric field. Okay. So if we just look at only a single direction, let's say only x direction, then from this relationship we can have is this kind of relationship. In here is that E reference is certain constant energy level. So we can treat that when we do the derivative in terms of this x direction, this is going to be 0. So we're going to have this kind of relationship. So in other words, if you look at this relationship carefully, when the potential has some variation in terms of position, okay, then we're going to have electric field. Okay. In other words, is for example, if you look at this kind of energy band diagram in here, and then let's say this is the x direction. Through the x direction, EC is a constant, okay, for this particular example. Then, as you can see from this equation, electric field going to be 0. Okay. We can choose instead of EC, we can choose the valence band too. So if we choose the valence band, we can have this kind of relationship. If we choose the intrinsic energy level, then we get this relationship. Okay. So EC, V, EI, there is following together, right? Okay. So that kind of the concept we can get from this equation. Okay. And then simply is that again is same thing, is the potential and then the electric field, the energy that related with the charge, right? So if we multiply charge with the potential, that gives us energy. Okay. So that is the important concept is we need to understand. So let's go back to this energy band diagram in here. Okay. Now is this energy band diagram. We see the two energy band diagram in here. One is called reverse bias, another called forward bias. The definition of this bias is when you have the PN diode, if you apply the positive voltage in the P side, that's we call the forward bias. If you apply the negative potential to the P side, that's we call the reverse bias. Okay. Now, as you remember, at the thermal equilibrium, is that we're going to see later on EF, Fermi energy level, going to be constant throughout this PN diode. Okay. And then over there is that when you draw the energy band diagram, you're going to expect that something like this. Okay, so this represents EV, this is represent EC, and then this side is P, and this side N. Okay, that is the we call the thermal equilibrium energy band diagram. So at the thermal equilibrium, one of the condition we can see is EF going to be constant throughout the structure. Okay, this one also we're going to later on in the other slide we're going to confirm this constant of EF. Okay, now for this thermal equilibrium, which means that there is no bias applied in here, in this PN junction diode, when you apply the bias, depends on the bias, we're going to have these two different energy band diagram. Okay, so the first, let's look at the reverse bias. So reverse bias, as I mentioned, is when you have the P N diode, okay, compared to the N side, if you apply the negative potential in the P side, okay, if you apply the negative potential in the P side, that is the condition we call the reverse bias. Okay, so now when you apply the negative potential in the P side, okay, so let's look at the thermal equilibrium. There is no bias. We know that the energy band diagram will follow this figure in here. If you apply the negative potential in the P side, okay, when you apply the negative potential in the P side, as I mentioned, this negative potential create the energy in the P side is going to be moved. Okay, and then as I explained, is when you apply the negative potential, all energy, this one moves upward in this direction. Okay, so in other words, is that if you just look at the reference in here, we're going to see that this kind of energy band diagram at the reverse bias. The EF in the P side, EF in the N side, they are not going to be aligned. They are not going to be constant because we apply the negative potential in the P side. So EF in the P side is going up, and then this increase of the energy represented by the you applied bias with this value. Okay, so that your new energy band diagram, when you apply the reverse bias, will follow this kind of structure. Okay. If we apply the forward bias, so when you apply the forward bias, now, as you know, when you apply the forward bias, your potential, the P side, going to be positive. Okay. So when you apply the forward bias in the P side, your energy in the P side is going down. Okay. So when this one happens, as you can see, if you compare the location of the EF in the P side and N side, the P side EF is moved down compared to the EF in the N side. Okay. So your resulting this energy band diagram follow this kind of curve. Okay. So that way is that you can draw energy band diagram when you apply the different bias. Can you understand this concept?
Could you explain again for both the reverse and the forward bias? So the energy, yeah.
Janie, somehow your voice is not clear. Can you say that again?
Sorry, is this better?
No, I cannot hear well.
Okay, all right.
Okay. Yeah, it's somehow distorted. I cannot hear your voice well. Okay, yeah, you can put your question on the chat. Okay, so Janie asked a question. Okay, that's good. So to understand this one is, as I mentioned, is that we need to go back for a moment. So when you have, for example, as I mentioned in the general, this energy band diagram, when you apply the negative potential, okay, the energy increase in this direction, okay. When you apply the positive potential, energy increased in this direction. In other words, this one is similar. We understand this way. When you have an electron, when the electron get the energy, they move to this direction. When you get the hole, for example, when the hole get the energy, then moves in this direction. Okay? So you have to understand first this concept. Now, applying this concept to this particular case, okay. For example, if you look at the forward bias, okay, and then look at the Fermi energy level, okay. So to understand this one is we need to first understand when there is no bias applied to the PN diode, your EF going to be constant throughout the structure, okay. So that represents you don't have any applied bias in the structure. Now, if you look at this energy band diagram in here, we can notice that the EF in the P side is actually lower than the EF in the N side, which means in here is to make the energy level lower in the P side. In here is that, as you can see, we apply the positive bias in this P side, so that the EF in the P side is lower. Okay. So similarly, if you look at the reverse bias, just to look at the location of EF. EF in the P side is compared to the EF in the N side is higher in this direction. Okay. So in other words, this one represents you apply the negative potential in the P side, and then the magnitude is this amount of magnitude applied in the P side, so that your EF is moved toward this upward in here. Okay. So can you understand is the concept? Yes. Because this is the important throughout the class. Later on is that we're going to have a different device. Is in this case is simply only PN diode, right? But let's say if you put another junction create the PNP transistor. Okay. So when we create this kind of transistor, now you can apply the different bias between this junction and this junction. Okay. So often when you look at this operation of this, for example, transistor, we're gonna go back to look at the energy band diagram. Okay. Then typically we look at the energy band diagram and then for different bias. So when you apply the different bias, you are able to actually draw the energy band diagram to the corresponding this bias condition. Okay. And then based on this change of energy in the particular region, you can actually draw the energy band diagram. Okay, that's good. And also in the semiconductor device when you look at the semiconductor device, especially potential distribution and electric field, the first step is to identify the electric field or potential for the given charge distribution. We have to solve the so-called Poisson equation in the structure. Okay. So the Poisson equation, general equation, follow the this relationship. So this one is again I just follow the notation in the book. This one represent the potential. Okay. So if you have a second derivative of this potential in terms of the position, this particular case we just look at only 1D. They're related with the total charge in that space divided by the dielectric constant. Okay, so using this relationship, now is later on we can calculate the potential and also electric field. Okay, so later on when we look at the p-n junction diode as an example, I'm going to come back this one and then explain how to solve this Poisson equation. Okay. Okay, then that's good. So first, before we go further, is that let me first explain that why is that the thermal equilibrium, or there's no potential applied to the p-n junction diode. The Fermi energy level should be constant throughout the structure. So as you remember, it's a basic concept of the p-n junction diode. When you form the p-n diode, okay, in the p side you have lots of holes, right? And then the n side you have lots of electron as the mobile charge. Now, because of concentration difference, initially is a hole moved to the n side, electron moves to the p side. So this movement is done by the initially concentration diffusion, concentration difference, and then this one we call the diffusion. Okay. Now, when the diffusion, this one happens, as you remember, is that now they're going to start to create the electric field. Okay. And then the electric field in here is especially in this region, we call the depletion region or space charge region. When the electron hole, they moving and then recombine, those events remains the corresponding dopant. So in other words, in the n side, your dopant ion is remain. In the p side, your negative, this dopant ion is remain. Okay. Now, this one is create the electric field in this direction at some point. And then the electric field is getting stronger as the diffusion is go further. And then at the end is now there is a balance between this diffusion and electric field. Okay. So due to this balance, when you look at the total current flow throughout the structure, the net current of this structure at the so-called thermal equilibrium going to be zero. Okay. So at the thermal equilibrium, we know that the net current of both electrons and hole across this diode junction is zero. Okay. So based on this concept, if we formulate this one in terms of current, we're going to have this kind of formula in here. Especially this one is, let's just look at the only hole current. Okay. And then also, to simplify this structure, we're going to just look at only x direction. Okay. Now, total hole current going to be JP. This represents the total hole current going to be one coming from the drift current, another one coming from the diffusion current. Okay. When you look at the drift current, as I mentioned, the origin of the drift current is coming from the electric field. Okay. So in other words, as you remember, if you have for example, is electron exist. Okay. And then if you apply the bias in here, then as you know, electron is negative charged. So the negative charge directed to the positive potential in here. Okay. So when the electron moves by this potential, or is simply, as you know, in this structure you have electric field. Okay. So when you have electric field in here, electron moves toward the positive potential side. Whole case move toward the negative potential side, right? So when this charge move, this movement create the so-called current. Okay? And then this current is we call the drift current. Oh, just 1 second. Just 1 second. Okay. Okay. So that creates the so-called drift current. Okay. Now, if you look at the drift current is carefully in here, as I mentioned, is that let's say electron or hole, they move, when they move, that create the current. So now when you look at the current related with is the first Q represent the charge. Okay. Especially for in here, hole is that the positive charge, so we just put this is a Q, plus Q. Okay. And then when the charge moves, that requires the mobility. This mu represents the mobility. So in other words, is that how fast this charge is moved. Okay. That represented by this mu in here. And then P, this one represents the number of holes. Okay. So as you can see, if you have 1 or 2, so this increase the number is directly proportional to your current. Okay. And then now is the electric field. Okay. So if we multiply the Q and then the mobility and number of this hole, with electric field, that give us drift current. Okay, so that's we can understand in here. And then another current is we call the diffusion current. Okay, so diffusion current is basically if you have the higher concentration of a hole, then that naturally move to the low concentration area. Okay, so when the high concentration of hole is, let's say, moved to the low concentration, the first part is, again, we're starting with a Q. So hole is the positive Q. And then the dP represent the diffusion coefficient. So in other words, is that how fast they are diffused. Okay. So this amount is determined by the diffusion coefficient. And then now, if you look at this one represents the concentration difference in the space. So for example, let's say this is the x direction in here. Concentration is, in here is high and then low, okay? So from high to low movement is that represent this diffusion, okay? So in terms of formula, high to low, this one is, now we can formulate with this equation. So P is the number of hole, and then dx is a derivative of this hole in terms of this x. So for example, if the P is a constant throughout the structure, then again there is no diffusion, so this term going to be 0. Okay. Now, if the P is a high to low, then this value is turned into the negative side. Okay. So to present that movement from the high to low, we put the negative sign in here, okay, to represent the diffusion happens from high concentration to the low concentration. Okay. So using these two equations in here, one is represent the drift current, another represent the diffusion current. So if we add them together, that's going to be total hole current. Okay. So as I mentioned, at the thermal equilibrium, this total current going to be 0. So we just put this total current as a 0, and then that represents at the thermal equilibrium. Okay. Now, in the following this derivation is we're going to show later on is that if we apply this one is in terms of EF, Fermi energy level, later on EF should be constant throughout the structure. Okay. So to do that is that we need one more equation in here to look at how this number of hole related with the Fermi energy level. Okay. So this equation, this one, represent the number of hole in terms of EF. So as you can see in here is basically, if you look at in here, the whole number P equals Ni represent the intrinsic carrier concentration. So for the silicon case, as you know, so Ni for the silicon is typically around 10 to 10, okay, and cubic centimeter, right? That's the number is typically we use, okay? And then exponential, you can see that the difference, energy difference between the EI and then EF divided by KT. Okay. So for example, is, as you remember in the previous, when you have an energy band diagram, this one represents EC, EV. around the middle, you have EI, okay? The EI, this one is, we call the intrinsic energy level. So in other words, is that when you have the different type of semiconductor, so for example, if you have N-type silicon, okay, as you remember, is that in this energy band diagram, if you draw the N-type silicon, the EF going to be close to the EC. If you look at the P-type silicon, your EF going to be close to the EV. Okay, so that way is that we identify whether energy band diagram represent the N-type or P-type. Okay. Now, as you can see, if the EF is equal to the EI, then that's we call the intrinsic semiconductor or intrinsic silicon for this case. Okay. So if you look at that one in here, and then combine that concept, when the EF is equal to the EI, then as you can see, is this term is 0. So exponential, this one going to be 1. So your whole concentration going to be Ni. Okay. So in other words, that the carrier concentration going to be Ni in here. Okay. That's the intrinsic carrier concentration. Okay. So that way is that we can understand this formula. Okay. Yeah. So using this formula, we plug in this formula instead of this P. We plug in this formula in here. Okay. And then we also do the derivative of this P, so that apply that one in here. Okay. So if we do the derivative, this P, whole concentration, then as you can see is Ni is the constant value, as I mentioned. EI or EF, that can be the function in terms of this X, right? So if you do the derivative, then you're going to have this kind of function. Okay. So now P and then the dP over dx, we put them together into this equation and then rearrange this equation. Then later on, we can obtain the following equation in here. Okay. From this equation, we can see that as a conclusion, to have the left side and then right side equal, we have to have is this term need to be 0. Okay. So in other words is we started this derivation saying that the total current is 0. So this means that we start from at the thermal equilibrium. So at the thermal equilibrium, as you can see, the change of EF in terms of this location need to be 0. In other words, is that when you draw the energy band diagram at the thermal equilibrium, the first step you have to have EF should be constant throughout the structure. Okay? So that way is that we can prove why EF should be constant, okay, at the thermal equilibrium. Okay. And then other thing is that this is also is we often see in the PN junction diode is we call built-in potential or built-in voltage. Okay. So when you look at the built-in voltage, built-in potential, now is this graph showing the energy band diagram in the p-n junction diode, especially at the thermal equilibrium. Okay. How we know is that we know the EF in here. Okay. So if we look at the EF, EF is constant throughout the structure. Okay. So which means that this represents the thermal equilibrium. Okay. Now, when you arrange the PN energy band diagram based on this constant of the EF, you will get this kind of energy band diagram of the PN junction diode. Okay. Now, if you look at carefully for this energy band diagram, first let's look at the P side. Okay. The P side location of the Fermi energy level from the EI, okay, that represent the number of hole. Okay. So in other words, if you go back, number of hole, this one represent by this separation, right? So from the EI to EF, if you have the more separation, then the number of hole going to be increased. Okay. So if you look at in here, this is the EI and this is the EF. Okay. So if you have more separation, this one, you have higher this hole concentration. Okay. So this separation represents the level of this doping in this side. Okay. So similarly, if you look at the N side, okay, EF minus EI, that represents the number of electrons. So similarly, if you look at the number of electrons, you can calculate from the Ni multiply exponential. Okay. In here is that the EF minus EI over KT. So using this equation, you can calculate the number of electrons. Okay. So same way, if this difference between the EF EI is larger, then again that increases the number of this concentration. Okay. So now is that if you look at the potential difference in the P side, N side, and then if you correlate these two difference, that difference is represent this barrier height in here. Okay. And then that is we call the built-in potential or built-in voltage in the PN junction diode. So in other words, is that the VBI, this one we can calculate from the potential difference between the EI-EF in the P side plus potential difference between the EF and the EI in the N side, and then add them together, that gives us this VBI. Okay. In here, this equation, we can also understand is, as I mentioned, is that the difference, for example, this one, related with the doping. Okay. So if you have higher doping, then this one going to be larger. So in other words, that affect your VBI. So when you make the PN diode, and then if you create with a higher doped, let's say, semiconductor, okay, then that one compared to the low doped semiconductor, this PN diode, this one will have the higher this VBI, okay, from this configuration. Okay, so that's we have to understand first. Okay, Now, second one is in here, is that, as I mentioned, in the conduction band, our interest is electron. Okay? In the valence band, our interest is in the hole. Okay? So now is, if you look at in here, okay, and then if you look at, for example, is EC, conduction band. Okay? In the N side, EC locate in this level. Okay? In the P side, your EC locate in this level. Okay. Let me ask a question in here. Okay. Which side has the higher energy in terms of electron? Is it P side or is it N side? Okay, Jamie said it's N side, and then any other opinion? Okay, P side is higher. So, okay, yeah, the correct answer is a P side is higher. So in other words, let's say, as I explained before, if you have an electron in here, when the electron get the energy, they move in here, right? So if we just look at the electron here, compare in here, the electron which is in the P side going to have this amount of energy. Okay? So that we have to understand in here. In other words, let's say you have in the N side, okay? In the N side is, as I mentioned, you have lots of electron, okay? Now is that if the electron is P side, of course, your majority carrier is not electron hole, so you have less electron there. So naturally, as I mentioned, is that the electron in the N side try to diffuse to the P side. Okay. But in this particular energy band diagram in here, as you can see, there is a so-called this kind of energy barrier is between the N side and the P side. So to move the electron from N to P, now whatever electron, they have this kind of energy. Those electrons can move to this P side. Okay. In other words, there is a energy barrier, and then the magnitude of energy barrier is in here, is as you can see, from here to here. Okay. So this kind of barrier is actually prevent the diffusion, further diffusion of the electron. Okay. So that kind of thing is you can also see from this energy band diagram. Similar concept is that we can also look at in terms of hole. Okay. So in the P side, you have lots of holes. Okay. Now, same way, if you look at the energy in terms of hole, now hole energy in the N side going to be higher than the P side. Okay. And then the magnitude of this energy is at this level. Okay. So as you can see, is that to move this hole in the P side to the N side, you require that this amount of energy barrier. Okay. So whatever hole has this amount of energy, they can move to this n side. But if the hole doesn't have this enough energy, they cannot move. Okay, that prevents the further diffusion of the hole in this direction. So that kind of information is we can obtain from this energy band diagram. Okay. Another one is I briefly explained is that the VBI related with the doping concentration of P side and then N side, right? Because if I go back, the VBI, built-in potential, we use the potential difference P side, potential difference N side. If we add them together, that gives us the VBI. Okay? And then each potential difference, they depends on their doping in the structure. Okay? So we roughly know is that the VBI related with the doping concentration. Okay. This slide formulate this built-in potential in terms of doping densities. Okay. So at the thermal equilibrium, now we're going to start with thermal equilibrium. Total hole current going to be 0. Okay. Hole current has the drift current and then diffusion current. So if you formulate from in here, or rewrite, then we get this kind of formula. Okay. And then in here is we have the important relationship between the diffusion coefficient and then the mobility. Okay. So they have the diffusion coefficient can be related with KT over Q and then mobility. Okay. So if we know the diffusion coefficient, from there we can obtain the mobility, or in other words, if we know the mobility, then using this equation, we can calculate the diffusion coefficient. Okay, and this one is, I guess you guys learned from 339. This one we call the Einstein relationship. Okay, so using this relationship is we rewrite the dp with the mobility in here. Okay, and then later on is the mobility we're going to cancel out in this equation. Okay, then final result is that you have this kind of relationship, electric field, and then your carrier concentration difference. Okay, so within this depletion region, if we integrate this both sides, okay, within the depletion region. So, for example, is the depletion in the N side edge and then P side. If we integrate electric field, this one represent later on is potential difference, or we call the built-in potential between the PN, this structure. Okay, and then if we look at this one we're gonna have this equation, KT over Q, Ln, and then the POP, and then the PON. POP represent is the P side hole concentration. PON represent N side hole concentration. Okay, and then typically is the P side hole concentration. We have the relationship with this equation. So for example, this one is a P side hole we call the majority carrier. Okay, and then the number of majority carriers related with their doping. So for example, in the P side hole represent we used Na, that's the dopant for the hole. So total number of this hole equal to the total number of the dopant. Okay, so we have this relationship. In the n-side hole represent the minority carrier concentration. Okay, and then minority carrier concentration we can calculate from this equation. Okay, and the equation this one represent Ni represent the intrinsic carrier concentration. So Ni square divided by your doping Nd, that represent the minority carrier concentration in the enzyme. Okay, so if we plug in these two to this equation, the final relationship in terms of VBI with the carrier concentration follow this equation. Kt over Q, Ln, Na multiply Nd divide by Ni square. Okay, so using this equation is you calculate your built-in potential. Okay. Let me double check. Is that in the 339, right? Question. You heard about the minority carrier and then majority carrier, right?
Yes, Professor.
Yes, right, Jenny. So, for example, N-type silicon, what is the majority carrier?
Electron.
Electron, yes. Okay. P-type silicon, what is the majority carrier?
Hole.
Hole, right? So same way, is N-type silicon minority carrier?
Say again, please.
What is the minority carrier for N silicon?
Hole.
Yes, right? Okay.
Yeah.
So you have to understand what is the majority carrier and what is the minority carrier, right?
Yes, sir.
And then, as you remember, is that using this equation, you can calculate the number of minority carrier and then the majority carriers, right?
Yes.
Right. So for example, let's say if I have N-type silicon, which doped with Nd is 10 to 17, okay, cubic centimeter. If I ask you what is the number of electron for this N-type silicon, then your answer will be
10 to 17.
10 to 17, right? Okay. And then if I ask you what is the whole concentration, then
10 to the third.
10 to 3, right? So if you, that one is that we assume that the Ni is 10 to 10, right? Okay. So this is the basic, I think, formula is later on is we often use throughout the different device. So you have to understand what is the minority carrier and what is the majority carrier. Okay, that's you have to understand first. And then before we moving next slide, if you look at the VBI, okay, VBI represent, as I mentioned, this is called the built-in potential or built-in voltage. Okay, that related with the doping. So in other words, is if you have two different type of p-n diode, one with a highly doped semiconductor, the other one with lower doped semiconductors. Okay. Then, as you expect from this equation, if you use a highly doped semiconductor, you can have the higher this built-in potential. Okay. So can you understand? Okay. And then another one is the built-in potential also related with the Ni in here. Okay. Ni represent the intrinsic carrier concentration. Okay. So if the intrinsic carrier concentration is higher, okay, then VBI in here is lower. If the intrinsic carrier is lower, then VBI going to be higher. Now, intrinsic carrier concentration related with the energy gap. Okay, between the EC and VEV. Okay. Typically, if the energy gap is larger, okay, then Ni is getting smaller. Okay. So if you have a large band gap semiconductor, okay, your Ni going to be smaller. Okay. If you have the lower band gap semiconductor, your Ni going to be larger. Okay. So in other words, is that if you just compare the VBI with the PN diode, which made with, for example, silicon, or if you have the, let's say, semiconductor with germanium, then different semiconductor will have the different this Ni. Okay, that also affect your VBI. So even though they use the same doping concentration, their corresponding VBI going to be different. So that kind of concept is you can also see from this equation. Okay. Okay, then that's good. So that is the kind of initial preparation is to look at this PN diode. Okay. Now, what I'm going to do in here is, as a simple example, as I mentioned, is to look at the exact electric field and potential throughout the PN diode. We need to solve Poisson equation. Okay. So in the following slide is basically I'm going to show you that how to solve this Poisson equation for the given this PN diode structure. Okay, so that's I'm going to do. Okay, so before starting further, do you have any question so far? So is it okay? Is it for you to follow the so far?
Yes. Okay.
Okay, then that's good. Yeah. So in case if I go too fast, it's always ask a question so that you can slow down. It's so you can follow. Okay. Okay. So if you do not have any further question, let me start in here. So what I'm going to do in here is, as I mentioned, we have the PN diode. Okay. So if we just look at the, let's say, only P-type semiconductor, okay, if we just look at the only P-type silicon in here is that as I explained, you have lots of holes available in the P-type silicon, right? So as a mobile charge, you have lots of holes, okay? And then each of these individual hole coming from their dopant, okay? So in other words, is that if you look at the P-type silicon as all this structure, if you measure the total number of charge, okay, total number of charge is that charge going to be 0, okay? So it's not the positive or it's not the negative. That is we call the neutral, okay? So even though it has the lots of charge, lots of mobile charge, okay, a total number of this charge going to be 0. Now, when you form the PN diode, as I explained, you have P, N, and then you have so-called depletion region. Okay. So within this depletion region, electron hole, they are moving and recombine, so they leave their dopant charge. So if you look at in here, P side hole moves to the N side, so that leaves this negative charge. In the N side, electron moves to P side, so that leaves the positive charge. Okay, so that kind of charge distribution you can actually see. So if we roughly present this charge distribution, you may expect the charge following this kind of graph. So in the P side, total number of charge going to be 0. Okay, and then the P side depletion region, your total charge is going to be negative. Okay. In the N side, your total charge in here is positive within the depletion region. And then the outside depletion region, your charge is going to be 0. Okay. So that kind of charge distribution you can expect. Of course, in here is that we assume is that the charge is abruptly changed within this depletion region. Okay. In reality, this charge distribution can be the different the variations. It can be linear or it can be some kind of function within the depletion region. Okay, but for this particular example, let's just assume we have this kind of charge distribution. Okay. Now, to obtain the electric field and potential for this particular case, as I mentioned, our starting point is Poisson equation. Okay, so Poisson equation relate your charge distribution to the electric field or potential. Okay, so in terms of electric field, particularly, we have this kind of relationship. Okay, especially this one is we just look at the 1D case. So derivative of your electric field going to be your charge divided by the dielectric constant. So if we look at this one is now the total number of charge within the semiconductor. In the last class, I explained that the total this possible charge going to be in the semiconductor either hole, positive hole, or negative electron. Okay, and then the hole, this one is coming from the dopant, negative dopant. Electron, this one coming from the positive dopant. Okay, so these four different elements represent all available charge in the semiconductor. And as I mentioned, hole and electron we define as the mobile charge, which means that they can move around within the crystal structure. The ND-Na, they represent the dopant charge, which actually bounded within the crystal structure. So that's we call the immobile charge. Okay, and then the sign is hole is the positive, electron is the negative, and then the corresponding this dopant is has this corresponding this sign. Okay, so that way is that we can represent all the available charge within the space in this semiconductor. Okay, So this is the first equation. This is we call the Poisson equation. Okay. And then second equation in here is that when the electron hole, when they move, okay, electron hole is when they move. Their movement corresponding with the depletion region is following this equation in here. Okay. In other words, in the 1D is that, let's say if you have the higher doped in the P side, okay, if you have the higher doped in the P side, okay, the number of hole moved to the electron to recombine represent the shorter this depletion region in the P side. Okay, so you have the depletion width with your concentration related with this relationship. Okay, so now is let's go back to this Poisson equation and then try to solve. Okay, so to solve this one is that we're going to actually split the different region. Is look at this equation. So the first is let's look at this region. In this region is x between the 0 to n o, which means that in the n side. Okay. So x equals 0. X and o is represent this depletion edge in the n side. Now, if you look at in here, is that the first equation, if you look at in here, this is the n side. Okay, so you can represent the whole concentration is close to 0. Okay, and then within the depletion region is that your electron is all recombined, so this is going to be 0. In the n side, so your Na is going to be 0 too. Okay. Over there, you have only Nd, right? So your equation to solve this one going to be electric field going to be Q epsilon Nd for this particular region. Okay. So if you solve this one and then integrate this equation, you're going to get this solution. Okay. C1 represents the coefficient to satisfy boundary condition. Okay. The boundary condition in here is we can assume is outside this depletion region. We say the electric field going to be 0. Okay. Then from that boundary condition, you can obtain this coefficient C1. So combine these two, now we get the electric field with this equation. Okay. So similarly, if you apply to the P side, especially in this location, between the 0 to negative this xp, okay, over there, your carrier concentration, this one is, as you can see, is only Na, negative Q Na available over there. So following the similar approach, if you calculate the electric field, then you get the electric field with this equation. Okay. And then using these two is, as you can see, we can have if we plot, we have the distribution of electric field of this equation in here. Okay. We have 1 minute left, so maybe I'm going to stop in here. And if you have any question, maybe I will take your question before we leave. Do you have any question?
Professor, yeah, one
Yes.
question here.
Okay.
Would it be correct to say that this particular example is an N-type PN junction.
This one is a PN junction, right? This is the PN junction.
Oh, okay.
Yeah, this is the PN junction. Okay.
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 Got it.
That's,
Thanks.
okay.
Mhm.
That's good. Okay. Okay. So I think one thing before you leave, as I mentioned, is that starting this week, I'm gonna check your attendance, right? So make sure attend the class because that's the count for 10% of your overall grade. Okay. So at the end of the class, I always look at the list of attendance. So from there, I can check your attendance. Okay. That's all. And then if you have any further question, then maybe we're gonna stop our class today in here, and then we're gonna continue Wednesday. Okay.
Thank you, Professor.
Okay. Thank you, guys. Okay. Be
See you next
safe and
class.
see you. Yeah.
Back home.
See you Wednesday. Okay.
Okay.
Mhm.